Okay, so most often you're going to see a problem that looks like this. A projectile is launched at 100 meters a second from a cannon that is set to 45 degrees from the horizontal. Many of you want steps, so the first step is going to be, I'm going to just tell you a little secret, you should probably Google it. And maybe we should close some of these tabs. Ooh, I probably should have looked at this before I started. Okay, yes. Just kidding. You probably could Google it, and you might get an answer, but I think the best course of action here to start out with is to write everything down that you already know and set this thing up on a coordinate grid. Okay, what we have here is we have our projectile at the origin. I kept the words of the problem on the screen so we could see it. I put the cannon below the origin. We want the projectile to leave from the origin. I wrote down the acceleration in the y direction is equal to little g, which is negative 9.81 meters per second. The initial velocity of the projectile is 100 meters a second. The angle of launch is 45 degrees. Displacement max x is going to be the maximum distance downrange that it travels. Displacement max y would be the maximum height that it achieves. The time to top is the amount of time it takes for the projectile to go from the origin to the apogee, or the very highest point. And then time total is the amount of time it takes to make the entire trip from the origin to the position on the x-axis where it lands. Okay, and just a reminder that gravity only acts in the y direction. So the velocity initial x will be the same as the velocity final x, but the y velocity will change throughout the course of the problem. Okay, let's draw our uncooperative vector. So this is our velocity initial. It's equal to 100 meters per second. This is set at an angle of 45 degrees. 45 does not jive with our x or y axis, right? It can't easily be measured. So we must break this up into its component vectors. So we need to use trig to calculate the x component. So the velocity initial in the x direction. I'm going to put that up here. And the velocity initial in the y direction. Okay, and these are cooperative vectors because the velocity initial x lines up with the x-axis, so I can figure out how long it is and I can measure it. And the velocity initial y lines up with the y-axis. We are going to be using trig to calculate this, so we want to write down SOHCAHTOA. And the reference angle here is 45. The side opposite 45 is the velocity initial y. So we know the hypotenuse, but we're looking for the opposite. So we can go ahead and use sine of 45 degrees is equal to the opposite, which is velocity initial y, over the hypotenuse, which is 100 meters per second. And like I always do, I tell you to cross multiply. So we do this, and we wind up getting sine of 45 times 100 is equal to the velocity initial y. All right, so I'm going to give you a real easy formula instead of doing all those steps. In order to calculate the velocity initial in the y direction, you are going to take the sine of the angle and multiply it by the velocity initial. And that will always output the velocity initial y. And then if you need the velocity initial x, same deal, which is going to be equal to the cosine of the angle theta multiplied by the velocity initial y. So essentially you're taking the velocity initial and you're just multiplying it by the cosine of the angle or the sine of the angle, and that's going to go ahead and output the x and y components. For the angle 45, they're both the same. The sine and the cosine of 45 are both equal to 0.707. That gives us 71 for the y and 71 for the x. So the best part about 45-degree problems, you only have to do one operation. You could just assume that the other one is the same. So that your x and your y components are both independent of each other, but they are related in terms of the time. So we're going to go ahead and fire the projectile. Nope. Pause. All right, so that's projectile at the top. Oh, I moved all these things. That's projectile at the top there, and we need to go ahead and calculate the total time to top. All right, so how we're going to do this is the total time to top has nothing to do with the x, right? So we're not even going to include it. But it does have everything to do with the y, because gravity's changing the value of the y all the time, but x remains constant. Okay, so we're going to say total time to top. How are we going to do that? Well, we might want to figure out, we might just solve it. We know the velocity initial, we know the velocity final, and we know the acceleration due to gravity. The trick here is that the velocity final is equal to 0. So the velocity y at the top is equal to 0, right? So we're going to treat this problem as if it were two problems. We're going to split it in half, and everything that happens on the upside is going to be different from everything that happens on the downside, right? So everything that occurs on the upside, we'll say velocity final y is equal to velocity initial y plus acceleration times time. So velocity final y at the top is 0. Velocity initial is 71, or 70.7 if you want to be really technical, plus the acceleration due to gravity times the time. So we need to solve this equation. We can go ahead and subtract 71 from this side, subtract 71 from this side. So we have negative 71 over here is equal to negative 9.81 times the time, right? And we're going to divide by negative 9.81. Times equal to roughly 7.1 seconds. And that's time to top. So what that says to me is that the total flight time is going to be about 14.2. The total time to top is 7.1. That means that it took 7.1 seconds for the projectile to leave the cannon and get to the maximum height. At the entire time that was happening, it was being robbed of its velocity by gravity at a rate of 9.81 meters per second. And so it took 7 seconds for it to run out of energy in the y direction. All right. So now we know the time to top is equal to 7.1. Awesome. The total time to top. That means that we can calculate the time total, right? So total time from there to there is 7.1 seconds. And then from there to wherever the object crashes is going to be another 7.1. Remember that projectile flight is like a mirror image. So what happens on one side happens on the other. Slightly differently, but generally the same. And we'll get into the nuances of that later. But total time to top is 7.1, which means that the total flight time, and I should stop saying total time to top. I should just say time to top, and I apologize. The total flight time is 14.2 seconds. 7.1 seconds up, 7.1 seconds down. All right, let's calculate the maximum displacement in the y direction. Okay, so we're going to go ahead and use this displacement formula. D equals VI plus VF divided by 2 times the time. We have to modify it, though. dy max is equal to VIY plus VFY divided by 2 times time top. If you don't use time top and use time total, you're going to wind up with a double displacement, because you're going to be saying that the object goes from 71 meters per second to 0 meters per second, and that occurs in a time of 14.2 seconds, which is not true. It takes 7.1 seconds for the projectile to get to there. And so if you said that it took 14 seconds, well, now you're talking about a much higher distance, right? Let's go ahead and solve this. dy max is equal to velocity initial y, which is 71, plus velocity final y, which is 0. That's at the top. Remember that vy is equal to 0 at the top, divided by 2, times the total time of 7.1 seconds, not 14. We wind up with a dy max is equal to 252 meters. So that's the maximum height. So that's how high the projectile travels, 252 meters, dy max, 252. Make sure we add all of those into our finished answer boxes. All right, let's recap the story a little bit. Cannonball is fired out of the cannon with an initial velocity of 100 meters per second, set at an angle from the horizontal of 45 degrees. Step 1 was we resolved our uncooperative 100 meter per second vector arrow into its cooperative x and y components by using trigonometry. And we made new formulas for that. We said that if you just take the cosine of the angle and the sine of the angle and multiply them by the velocity initial, that will give you the x and y components. So instead of going through the SOHCAHTOA process. Anyway, so x and y are independent of each other. X, the object initial velocity in the x direction, is equal to 71 meters per second. That does not change. The velocity in the y direction, initial, is 71 meters per second as well, and that does change. It's affected by gravity. It takes gravity about 7 seconds to deplete that energy, and the projectile momentarily loses all y velocity at the top of its flight. That process takes about 7.1 seconds. So the ball is now at the top of its flight, and we've completed one half of the problem. Okay? A couple of things you need to know is that the projectile will continue to fall for another 7.1 seconds until it impacts the ground at 14.2 seconds. So let's go ahead and calculate the total downrange distance that the projectile traveled. For this step, we can just use the displacement equation with no acceleration, or the velocity equation, whatever you want to call it. But again, we want to add little markers to it to indicate that it is done entirely with x numbers, right? The velocity initial x doesn't change, so we're just going to call that velocity x. The total time is useful here. If you used just time top, you would only get the distance from the cannon to the middle of the flight in the x direction. And you don't want that. You want the total distance. So displacement x is equal to velocity initial x, which is 71, times the time total, which is 14.2 seconds. So when I do this equation, I get 1,008 meters. So the total displacement x is going to be equal to 1,008 meters. 1,008. All right, so again, let's tell the story. Projectile is launched out of a cannon, initial velocity 100 meters per second, set at an angle of 45 degrees. We use trig to break that into its x and y components. The projectile leaves the cannon with an x component of 71 meters per second, a y component of 71 meters per second. Gravity affects the y component only, depleting the energy in the y direction in about 7 seconds. The projectile continues to move to the right for another 7 seconds and crashes into the ground 1,008 meters downrange, 14.2 seconds later. And because we know things about physics, we also know the crash angle and the crash velocity, right? So the projectile will land at the same angle that it was launched at, and it will crash with the same downward velocity and the same over velocity. However, in this case, instead of the velocity being 71, it would be equal to negative 71. Okay, that's pretty much it. I was not hyper organized here when I was drawing out this stuff, but hopefully you can develop your own organizational system. If you're not really sure what to do, I always recommend that you make yourself a box. You make yourself a box, and this just says all of your Y stuff in it, and the same thing, all of your X stuff on the other side. Okay, let's do some practice problems, and I'll give you the answers later. So, number 1, I don't know. Let's say a projectile is launched at 38.4 meters per second, and the angle of that projectile is 21 degrees. And so I want you to find, displacement x, displacement y, time top, time total, and of course, your crash velocity and your crash angle. All right, yeah, get that done. And number 2, figure out how to clear my internet search history. Just kidding. I want to go ahead and give you, let's say a 383 meter per second projectile, and that would be at an angle of 88 degrees, just like Doc Brown.